Hi, this is part one of a three-part unit on oscillations and waves. All the images and figures that you'll see in this video are attributed to OpenStax College Physics, a textbook distributed by openstax.org under the Creative Commons Attribution License version 4.0. Oscillations are a very important type of motion that we see every day. For example, a child swinging back and forth on a swing, a pendulum of a clock swinging back and forth. We're going to begin by studying oscillations by considering a special type of oscillation or vibration that's called simple harmonic motion. And what makes simple harmonic motion special is these are oscillations that are governed by forces that depend directly on how far the oscillating object is displaced from some special position called the equilibrium position, and the force that's pushing and pulling on these objects is always directed back toward this equilibrium position. So we call this a restoring force. A really good example of a system that follows these two rules are systems that involve springs. Here, let me show you. Here's the spring. If I hold the spring steady, we can call the position of the end of the spring its equilibrium position. If I pull the spring away from its equilibrium position, the spring force pulls back. So the spring force is a force that's always directed back toward the equilibrium position. Another property of the spring force is it gets stronger. Anyone who's ever stretched a spring knows that the spring force gets stronger the more you stretch the spring. So, oscillations that involve springs are good candidates for modeling using the theory of simple harmonic motion. We're going to look at two example systems that exhibit simple harmonic motion. The first is a mass vibrating on a spring, and the second system is a swinging pendulum, which has many similarities to masses vibrating on springs. When we look at the mathematical descriptions of these systems, pay attention and be aware of the assumptions that we're making when we write down these mathematical equations for modeling these systems. Okay, let's take a closer look at our first example, a mass that oscillates on a spring. When we look at this system, we're going to assume that the spring obeys Hooke's law. You may remember Hooke's law from last semester. Hooke's law says the restoring force exerted by a spring, is proportional to some constant K, which is called a spring constant. And the spring constant is a measure of how strong the spring is. A strong spring has a big K, a weak spring has a small k. And X is how far the spring is displaced from its equilibrium position when it is at rest. Okay, so we're going to assume that our spring obeys Hooke's law, and we're also going to assume that our system experiences no friction and no drag. Okay, so we are going to look at, I'm going to show you some demonstrations of a mass oscillating on a vertical spring, and then after we do that, we're going to look at the mathematics of a mass oscillating on a horizontal spring. So when we do that, here's a question for you to keep in mind. When we look at the vertical spring, the force of gravity is a force that is important and exerted on the mass and the spring. So why can we ignore the force of gravity when we write down the mathematical equations that describe masses oscillating on springs? Because these equations that we write down apply to masses that oscillate vertically or horizontally. So we can ignore the force of gravity, and that's something for you to think about. I'm not going to give you the answer to that. Before we look at a demonstration of masses oscillating on springs, there's a few definitions that you need to know. When we're talking about oscillating systems, the period for an oscillating system is the amount of time, t, between successive occurrences of the same state of the system, which includes position, velocity, acceleration, etc. So when you're measuring the period of an oscillation, You measure how long it takes the oscillating body to return to where you started timing its motion. Frequency is the inverse of period. And we can think of this as the number of cycles or vibrations repeated in a given interval of time. Finally, amplitude for an oscillating system, and we'll use the capital letter X to represent amplitude, is the maximum distance an object travels away from its equilibrium position. And again, equilibrium position is the situation where little x equals 0. Displacement equals 0. So let's take a look at some masses oscillating on springs, and let's make some observations about how they behave. Okay, the first thing we're going to look at is how the spring constant influences the speed of the oscillations. So what I have here is I have two springs. This is a particularly stiff spring. It's a strong spring. It has a large K, a large spring constant. This is a weaker spring. It has a smaller spring constant. Okay. What I'm going to do, and from each of these springs I have hanging a 50-gram mass. I'm going to perturb the springs from their equilibrium position where they are right now. I'm going to stretch them, and we're going to observe the oscillations. You want to make a prediction? Which one is going to oscillate faster? Which one is going to have smaller period, higher frequency? You ready? Let's try it. So it's very obvious. This spring, with the larger spring constant, has a much higher frequency, a much smaller period. It makes more oscillations per second. Okay? So everything else being equal, a larger K means a smaller period or a larger frequency. Okay, let's try something else now. Let's see how the period and frequency of the oscillations depend on mass. Okay, so what I'm going to do, let's stick with this guy over here. Okay, so with 50 grams oscillating up and down, we have oscillations that look like that. Let me add 100 grams. So now we have a total of 150 grams. We have oscillations that look like that. Let's add another 100 grams. We have a total of 250 grams. We have oscillations that look like that. So we see that there is a mass dependence on the speed of the oscillations. The general observation here is the greater the mass, the slower the oscillations. The larger the period and the smaller the frequency. Slower oscillations, greater mass. All right, let's do one more experiment. What about amplitude? Let's see how the speed of the oscillations depend on the amplitude. So I'll use this spring, the one with the smaller spring constant, perturb it, get it going. I can time the oscillations. The period would be how long it takes to go from one point where it has, let's time the period from its lowest point until it returns to its lowest point again. So I get 0.75 seconds. Now let's see what happens if I have an oscillation with a smaller amplitude. .79 seconds. So within the margin of error of my measurement here, it's the same. What about a larger amplitude oscillation? .77 seconds. So again, the same. So what we see is the period of the oscillations, the frequency of the oscillations does not depend on the amplitude. but does depend on the mass hanging from the spring and also the strength of the spring constant. Okay, so let's summarize what we just observed. We observed that the period got bigger as the spring constant got smaller, or the frequency got smaller as the spring constant got smaller. We also observed that the period got larger as the mass got larger, or the frequency got smaller as the mass got larger. And amplitude didn't have any effect at all. Okay, so keep these observations in mind as we derive mathematical expressions to describe this system and what's going on. So let's talk about the mathematical form for the kinematic equations describing simple harmonic motion. And it turns out that if you plot the position of a mass oscillating on a spring as a function of time, that position as a function of time will look sinusoidal. If we look at this example here, the position as a function of time for this ball oscillating on a spring follows a cosine relationship, where the position at any given time t is equal to the amplitude of the oscillation times the cosine of this function, which depends on time and also the frequency of the oscillation. Similarly, the velocity and the acceleration also exhibit sinusoidal relationships. In this particular example, the velocity as a function of time is proportional to negative some maximum velocity, which can be thought of as the amplitude of the velocity, times the sine of 2 pi ft. And the acceleration can be written as negative a max. Again, you can think of that as the amplitude of the acceleration function times the cosine of 2 pi ft. So all of these kinematic quantities, x, v, and a, can all be expressed using sinusoidal, that is, sine or cosine functions. So now let's make an interesting observation. It turns out that these sinusoidal functions describing simple harmonic motion, like the mass oscillating on the spring, are exactly the same types of equations that you would get if you took uniform circular motion and projected it from 2 dimensions onto 1 dimension. And a good way to, what does this mean? Well, picture, like right here, you have a little red ball that's undergoing uniform circular motion. If you put a bunch of spotlights above that ball and projected the shadow of that ball onto a piece of paper that's rolling by, and this is making a mark on this paper, the shadow of the ball would trace out a sinusoidal function. And the mathematical equation describing that sinusoidal function would be exactly the same type of equation as what we wrote down on the previous slide. So what this actually allows us to do is take something we know about uniform circular motion and apply it to the case of simple harmonic motion. And that thing that we know allows us to write down an equation for the speed, or more specifically, the maximum speed of a mass undergoing simple harmonic motion. So let's begin by writing down an expression for the speed of a particle undergoing uniform circular motion. Speed is for a particle undergoing uniform circular motion is the circumference of the path that the particle is following divided by the period for 1 revolution. So we can write that as v equals 2 pi r. 2 pi r is the circumference of a circle, where r is the radius of the path, divided by a capital T. So what's the connection between the radius of a particle undergoing uniform circular motion and the amplitude of this projection of the motion onto 1 dimension? Well, the answer is the radius is equal to the amplitude. They're exactly the same. This allows us to substitute x for r into this expression. And another observation is when we project uniform circular motion onto one dimension, we only get one component of that motion. And if we take a look at the vector for the velocity of a particle undergoing uniform circular motion, like I've drawn up here, we can think of that vector as having an x and a y component. So when we project this motion, uniform circular motion, which is two-dimensional, onto one dimension, all we see is the x component. So this means whenever the object undergoing uniform circular motion is at the top or the bottom of its path, like it is right here, all of its velocity is directed in the x direction. And the projection of this motion onto one dimension would exhibit the greatest speed, v max. So where the v occurs in the speed of the particle undergoing uniform circular motion, when we project that onto one dimension, that becomes v max. Okay, let's take a look at simple harmonic motion from a different angle. Let's take a look at it by considering the energy of the mass oscillating back and forth and apply conservation of mechanical energy, which we can do because remember earlier we made the assumption that this system has no friction and no drag forces. So mechanical energy will be conserved. None of the energy is dissipated as heat, as thermal energy. So, in the real world, this is not strictly the case. So this is an idealization of the types of motions that you would exhibit in the that you would see in the real world. Okay. So the picture that you see on this slide are like snapshots of a mass oscillating horizontally back and forth on a frictionless platform driven by a spring that stretches and is compressed. And each of the pictures represents what the mass spring system looks like at a different moment in time. So this picture, the first picture, call that A, shows a situation when the mass is at its greatest displacement, x equals capital X, the amplitude. The picture labeled B here shows the mass as it swings back through its equilibrium position, x equals 0. Panel C shows the mass when it's at its greatest displacement in the negative direction, x equals minus capital X, the negative amplitude. And panel D shows the mass swinging back through the equilibrium position again, or being pushed back through the equilibrium position again, x equals 0. And then the process repeats. In panel E, the mass has returned to where it started in panel A, so it's completed one complete oscillation. The amount of time it would take to complete this one complete oscillation would be the period of the oscillation, and 1 over this time would be the frequency of this oscillation. We learned last semester that mechanical energy E is the sum of kinetic and potential energy. Kinetic energy is 1/2 mv squared, and last semester we learned that the potential energy stored in a spring is equal to 1/2 times the spring constant times the displacement from equilibrium x squared. So in panel A, there's something special happening. In panel A, the mass is at its maximum displacement from equilibrium in the positive direction, x equals capital X. And when this is occurring, the mass is in the process of changing direction, and at that moment, its velocity is 0, its speed is 0, and its position is capital X. So in panel A, the mass has mechanical energy, but all of its mechanical energy is potential energy. Because its speed is 0, it has no kinetic energy. That's true in panel C as well. In panel B, something else is happening. In panel B, the mass is at its equilibrium position, x equals 0. And what do we know about Hooke's law? Hooke's law says the restoring force is proportional to the spring constant and multiplied by the displacement from equilibrium position, x. So if the spring is at its equilibrium position, the force exerted by the spring is equal to 0. So that means when the mass is passing through its equilibrium position, like it is in panel B and panel D, there is no force exerted on the mass. So it's not accelerating. F equals ma. So if F is 0, A is 0. It's not accelerating. So at that moment, it's not speeding up and it's not slowing down, but it has the highest speed that it will attain anywhere, V max. So while its position is 0 and thus the potential energy stored in the spring is 0, the kinetic energy is maximized, equal to 1/2 m V max squared. So in panel B, there's no potential energy. All the energy is kinetic energy. Okay, so let's put this all together. At any moment in time, the mechanical energy of the mass oscillating on a spring is equal to the sum of the kinetic energy and the potential energy. But we see that at two spots in the motion, namely x equals capital X, the maximum displacement from equilibrium, and x equals 0 when the mass is at the equilibrium position, one of these terms is going to be 0. So we saw when the mass is at its maximum position, all of its energy is potential, and x is equal to capital X. When the mass is at equilibrium position, all of its energy is kinetic, and V equals V max. So the power of conservation of energy, or in this case, conservation of mechanical energy, is that we can set the energy that the mass has at a moment in time equal to the energy it has at any other moment of time. So if we look at these three equations, we can set any of those equations equal to any of the other two equations, giving us a whole bunch of mathematical relationships that we can use to solve interesting problems. For example, one thing we can do is we can set this equation equal to this equation, and we can find that there's a relationship between the maximum speed attained by the spring, the mass on the spring, and the maximum amplitude of the mass oscillating on the spring. 1/2 k x squared equals 1/2 m V max squared. So we got to be careful. This is a capital X, where little x is equal to capital X, the amplitude. And there's a 1/2 on both sides, so they cancel. So we're left with, get my pen back here, k capital X squared equals m V max squared. Okay, so using conservation of mechanical energy, we can find this relationship between the amplitude of the oscillations that are occurring and the maximum speed. So this should make a lot of sense. If you have a mass attached to a spring and you set it to oscillate by perturbing that mass, the more you perturb the mass, the greater the amplitude of the oscillations, the faster it's going to be moving when it passes its equilibrium position. All right, to wrap up this mini lesson, let's combine what we just learned about masses oscillating on springs undergoing simple harmonic motion when we consider the mechanical energy of that system with what we learned about simple harmonic motion as a projection of uniform circular motion from 2 dimensions onto 1 dimension. Okay, so I've rewritten the equation that we got by considering how simple harmonic motion looks like uniform circular motion. And that allows us to write down this equation that says the maximum speed attained by an object undergoing simple harmonic motion, like a mass oscillating on a spring, is equal to 2 pi times the amplitude of that oscillation divided by the period. And I've also written down the expression that we got by considering the mechanical energy of a mass oscillating horizontally on a spring, and more specifically by setting the total energy that the system has when the mass is at its equilibrium position, 1/2 mv max squared, all kinetic energy, equal to the mechanical energy that the mass has when it's at its maximum displacement from the equilibrium position, x equals capital X, the amplitude of the oscillation, 1/2 k x squared. And the 1/2's canceled, so we're left with k capital X squared equals m v max squared. So what I'm going to do is I'm going to combine these two expressions into one expression that gives us a relationship relating the period of the oscillations of a mass on a spring to the spring constant and the mass of the mass oscillating on the spring. So to do that, what I'm going to do is I'm going to, what I did first was I solved the second equation for Vmax by dividing both sides by m and then taking the square root. So I get Vmax equals the square root of k over m times capital X, the amplitude. So now I can set this term equal to this term, giving me 2 pi over t x equals the square root of k over m times x. So an interesting thing happens here algebraically. There's a capital X, the amplitude of the oscillation is on both sides, so it cancels. And so what we see is that in the end, we're going to have a relationship where the amplitude doesn't matter. And that's exactly what we saw in those demonstrations at the beginning of this lesson. So if we do a little bit more algebra and solve this equation for t by multiplying both sides by t and then dividing both sides by the square root of k over m, which gives you the reciprocal m over k, square root of m over k, we get a final relationship giving us the period of a mass oscillating on a spring as a function of the mass and the spring constant. And what we see is, again, the period does not depend on the amplitude. There's no capital X in this equation. That's exactly what we saw in the demos earlier. The period gets bigger as the mass gets bigger. Again, we saw that in our demonstrations at the beginning. And the period gets smaller, the oscillations get faster, if the spring is stronger, if k is bigger. If we want to look at the frequency instead, the frequency is 1 over the period, which gives us frequency equal to 1 over 2 pi times the square root of k over m. So as the spring gets stronger, k gets bigger, the frequency increases. The oscillations happen more quickly. As the mass suspended on the spring gets bigger, the frequency gets smaller. The oscillations happen more slowly. So this concludes the first part of this 3-part unit on oscillations in waves. And the main takeaway for this part of this unit are the equations that are in the bubbles on this page. The equation giving you the period of a mass oscillating on a spring and the frequency of a mass oscillating on a spring as a function of the spring constant and the mass. Thank you.